In this segment, I want to talk a little bit about optical instruments. In a way, there's no new physics in Chapter 19. In a way, it's just an application of the physics that we learned in Chapter 18. In Chapter 18, we learned how images are formed under various circumstances, whether it's just from a flat piece of glass or a flat-sided aquarium, or from lenses or from mirrors. Now, what we can do is we can put a couple of lenses together or put a couple of mirrors together and end up with a much more sophisticated apparatus than with just a single lens or a single mirror alone. And the possibilities are almost endless. We're just going to talk about a couple of applications in this chapter. The first is just the camera. And it turns out that a camera is a fairly straightforward device. And we all walk around with these lovely digital cameras in our pockets. And really, a camera is really just a single lens system. And so that's why we're going to start with that. And the basic idea is you've got some object here that you're trying to focus an image of. And this light passes through a lens and is collected and focused onto some screen. And this screen, in the old school days, it would have been film. Nowadays, of course, it's an electronic detector of some sort. That's the basic idea. Now, the detector that you have is made up of pixels, right? And so these are just tiny little squares where we collect this information. Of course, if you zoom in, you start to see that each one of these squares is a specific color and a specific tone and a specific brightness, right? And if you put them all together in the aggregate, you get this nice picture. So a CCD, it stands for Charge Coupled Device, and it's really a quantum mechanical device, which we're not going to talk about too much right now. So a photon, if it strikes one of these pixels, it causes it to record an event. And then the computer basically reads off all of the pixels where a photon has struck and can recreate an image. That's the basic idea of a charge-coupled device, or a CCD. So recall a lens here. This is just a single converging lens, and this is the basic operation of a camera. Here we see our object, and we form this image right here. Now the focus of the camera is achieved by moving this lens. And so by moving this lens, we make sure that the image plane and the film, or the CCD, are right in the exact same location. So notice here, if we were to put our film or our CCD at A, we'd end up with a blurry image. If we were to put it at C, we'd end up with a blurry image as well. It's only when we have it right in the image plane where we would get a nice, well-formed image. The thin lens equation, which also works for mirrors, describes this situation. It's important to note here that this is a real image that's formed right here. Only real images can create can expose film or make a charge-coupled device do its thing. Why? Because the light actually has to converge at this location. So you can only take a picture of a real image. You cannot use a virtual image to take a picture. You cannot expose film with a virtual image. All right, let's do this example real quick. In the figure, the camera lens has a 40 millimeter focal length. How high is the man's well-focused image on the film? Now, they give us the height of the object, 2 meters. Which means that in order to figure out how high the image is, how tall the image is, we need to figure out the magnification. So what else did they give us? Well, they also gave us the focal length. It says it's 40 millimeters. We know that a converging lens, a convex lens, has a positive focal length, and that's what we're dealing with here. So we should write 0.04 meters, positive, because it is a converging lens. And notice also in the image, they give us, in the picture here on the PowerPoint, we are given the object distance. 10 meters. Okay, so we are then going to want to calculate the magnification, which is negative s prime over s. In order to do that, we're going to have to calculate what s prime is, right? So we could do that using this equation here. we're going to want to solve for s prime. Find the common denominator. Flip both sides upside down. So now we can just plug in our numbers. S prime then, plugging into that equation right there, is F times S, 10 meters, divided by S minus F. Now, notice here that my denominator doesn't change very, very much, right? So, really, these rays are coming in almost parallel to the camera, right? And so we're getting a converging set of rays at basically the focal point, because this doesn't really change much. In fact, to two significant figures, we end up with an S prime of 0.04 meters. Okay, now let's calculate the magnification. So it's negative S prime divided by S. We get 0.04 for our magnification. And it's negative. What does the negative indicate? The negative indicates that my image is upside down. But we actually knew that. We learned that in the last chapter. We learned that a single converging lens forms an image that is upside down. And we also learned that an upside down image is always a real image in a single lens system. So indeed, we have it's inverted, and it's much smaller, isn't it? Our magnification is 0.004. So recall that the absolute value of the magnification is h prime over h. And so we get that h prime is equal to 0.004 times 2 meters. That gives us 0.008 meters, or 8 millimeters. That's a reasonable idea. And it is upside down.